Let me tell you all a tale with the speed of light, and a vacuum, of course. This is actually an Ohms tale. Yes, I've been away for a bit. I've been pondering some stuff and things. Y'all know what that means. We conjecture ahead.
Although this is going to be weird, and it's going to be about a different.
Title of the conference was something like Ground Truth or Turtles All the Way Down. And so it seems as though there's one Ruliad. I don't think it rules them all. And it might be just hyper-rulial turtles all the way down.
Yes, it's on the back of an infinite number of hyperrulial turtles.
Various people are commenting on the outrage of hacking the universe on a MacBook Air.
Hey guys, what's going on? Means here. I apologize. I've been away, especially to Fizz. I got on my science thing on Thursday. I completely forgot about our show. I always. Now, speaking of stuff and things, what happened? Well, essentially what had happened is I got on a little buzz because at one point we have that 10 to the negative 7, technically negative 8, blah, blah, yeah. At the 7th decimal place, there's a deviation there. I was asking Thad about when does special relativity kick in? It's like, oh, around 85% of the speed of light. I'm like, all right, I'm checking something. So I'm like, I multiplied the speed of light by that thing. And then I look at the numbers, I'm like, that looks very similar to something I saw before. Is it Ohms? I'm looking for Ohms and stuff, and that's like, is it Ohms? It's, oh wait, which of the Planck thingy? Impedance. I looked it up. I'm like, is that 29.9? I looked, I'm like, it was like the same as like the speed of light. And I looked up Ohms, and we have an extra digit. I found that fascinating, so I've been playing around. But hey, Upcycle, welcome. Thank you for joining my friend. To you, as well as all those who may join temporally in the future. Thank you. But what are we talking about today? Today, we're talking about impedance, specifically more of the electrical type. Even in Wolfram Alpha, you go to impedance, and where is it? Blah, blah, blah. Assuming impedance is a physical quantity. Mechanical impedance, mass divided by time, Newton per meter per second. I'm like, that's interesting. You click on electric impedance. It gives you a definition. I'm like, what? Shouldn't this be going to something else? Okay, thank you, Wolfram Alpha. Now, yes, I totally got my thumbnail from here because, thank you, Vox. The key to tackling climate change. Electrify everything. We thank you for your Shutterstock thumbnail. So, hey, Neutrino and Kali. I forgot to reach out to you. I apologize. I've been binging this. I got my notebook all set up, all nice and cool, and then I apparently had a kernel error. I thought I just inquired to. It was my fault. I didn't follow the Wolfram instructions. I just quit the kernel, started the thing, and everything was fine. I need to close the actual things in the browser. That's a technical issue. These things happen. But, all right. So at least according to electrical engineering, we'll just... Impedance is the opposition to alternating current, presented by the combined effect of resistance and reactance. What the heck is reactance? In electrical circuits, reactance is the opposition. That's basically what we just said. Oh, it's almost like there's a stiffness going on with the things in the realm in which we exist in a circuit. Quantitatively, the impedance of a two-terminal circuit element is the ratio of the complex representation of the sinusoidal, some waves and stuff, cool voltages between its terminals, to the complex representation of the current flowing through it. In general, it depends upon the frequency of the sinusoidal voltage. I'm not an electrician or an electrical engineer. Yes, I am reading from Wikipedia, take it for what it's worth. But see, they have electromagnetic pictures and stuff, and where is it? Oh, complex impedance plane. There seems to be an angle there. We'll get to that later. But, yeah, no, it's... Well, this is the thing. I've been avoiding learning this. I've listened to some of Eric Dollard's things where he composed all these things for 4 hours and stuff. I feel like I need to listen to some of those things, or at least read some of Steinmetz's paper. I hear that's very valuable because there's another version of the Maxwell equations that maybe we don't use as much. But we go back to, again, part one. There's a whole other notebook where we do a lot of the same things, but we also do some different things. But neutrino. Like, one of the reasons, at least for some science stuff, I'm like Wikipedia. It's one of the few places I'm like, I will send you some cash here or there for a donation because I use it. When I watch Team Wolfram, just cursory think, what is this? They go through it. I'm like, okay, yes, trust, but verify. The speed of light and back again. An Ohm's tail. Yes, okay. So some very basic things you can do. And the link is in the doobly-doo before if anyone wants to follow along. All right, so you can literally just do this on Wolfram Alpha 2. C. Assuming C is a unit. Okay. Oh, look, the speed of light gives us this thingy here. All right, what? 299, 792, 458 meters per second. Groovy. Speed, length over time. Because that's what the -1 means. It means you put in the denominator. It's easier to, or it's easier to just plug it in for the dimensions. All right, so we did 10 to the -7. We'll get to the more precise, at least according to our current Planck unit constructions. All right, speed of light to the -7. That's what happens when you basically put the Planck mass times the Planck length divided by the Planck charge squared. That's the inversion boundary in the HF8 model of the minimal arena we're working with here at the monastery. Okay. Okay, so it gives us basically meters per second, but it went down to this number here. I'm like, okay, that number looked familiar. So I'm like, what might that be? The Planck impedance. What is this number? So it's that 1 over 4 pi times the speed of light times the electric constant. Okay. Wait a second. This number looks eerily familiar. Wait a second. 29.97924582. I'm like, okay. Wait a second. What was the speed of light? Da-da-da. Wait a second. 29. This is to the 7 decimal points with a 1. You basically move the 7 decimal points over. I'm like, 29.9792458. And at ohms, we have an extra significant digit. That's very interesting. So okay. I found that fascinating. I'm like, why might that be the case? Okay. So we have these, here are the dimensions for impedance. For us to get to ohms, we take mass, multiply it by length squared, and then these -1s, you put them in the denominator. It's time to the 3, or -3 for the denominator, and current to -2. There's another expression, basically current is charge divided by time. So we'll see this in our little calculation here. So we have our little calculation. Okay. So what do we have here? Okay. So again, on the top part of the thingy, don't worry about the numbers. Just be like, technically you could probably set them to 1. A lot of folks, we're just doing this so we can show some receipts. Isn't that what the kids say nowadays? Now, moving right along. So this corresponds to the Planck mass, as you see, kilograms. It's our Planck unit there. This is in meters, so that's the Planck length. We square that. And then we have seconds, raised to the 3 there. And then this is basically current. Current is charge divided by time. So Planck charge divided by the Planck time. And we square that. Fits into this neat little thingy here. Gives us this calculation. I was initially happy with this calculation. This is not the number we saw. It deviates after this too here. So, okay. More investigation was required. Let us continue. Is this the same thing? Yes, I have that again there. Just for retention's sake. All right, so our inversion boundary, the actual calculation. You take your Planck length here, you multiply it by the Planck mass over the Planck charge squared. Of course, I can't spell coulombs right, but Wolfram Alpha is smarter than me. It's always good to have friends like that. Okay, so it gives us this. So This is not 1. This is very darn close to 1, but it is not 1. Maybe it is actually 1. But as we can see, we have 1, 2, 3, 4, 5, 6. Oh, look at the 7th significant digit. Things start to get a little interesting. Hey, Nathaniel. Like if I joining my friend? Thank you, sir. All right. So where are we here? Okay. So -8, because if it was 1, it would be -7. Okay. Magnetic permeability. So we got mass length, time -2, current -2. Yes, because time is, charge squared. That's what it breaks into. All right. Since that number wasn't exact, we did a calculate. Literally, I just did a calculation. Took me a while. We did some searching. I got one really good. I got at least a couple really good ones. So we'll go there. But, all right. So the Planck impedance calculated. We're not to that yet. We're going to multiply that by the inversion boundary. This was another cool thing. So basically that inversion boundary right there, approximately 1 ampere, constant. You want to have the constant there because I put 1 ampere in there before and I'm like, why are these numbers going all crazy? Why is it not doing it? It's a different thing. You want to add the constant to it. So the Planck impedance calculated times our inversion boundary there. Okay. So basically when we take this, okay, don't worry. It's just stuff doing things. Don't worry about the numbers, except when we're actually checking them. Okay, so over here, we basically have our ohms, and then we have the big division sign here. So we're dividing that by this, so our inversion boundary. And then it gives me this number here. I'm like, wait a second. Because I look at dimensions, and I'm not a wizard like Thad yet, but I'm like, these dimensions should cancel out to something interesting. Wait a second. 2.99792, yada, yada, yada. The yada isn't correct. But times 8 meters per second. Huh. That seems to be the speed of the light, too. 1, 2, 3, 4, 5, 6, 7. Okay. To be fair, we should probably do 7 there. Yeah. We know the speed of light to 9 decimal places. So there is we need a correction term here. How can we get there? Okay. The speed of light, according to the current model that we have here at the monastery, is basically you take your dimensions of the length divided by time. According to these, this will get you to about 7 decimal places. And then we have our terminal action, because interestingly enough, right around 7 decimal places, things seem to get a wee bit wonky at times. So we need to de-wonkify. How do we do that? The particular answer that we have here is 1 plus or minus our terminal action here. The terminal action is the square root of the minimal 3 manifold, the Giesking manifold, times times J1 minus J2. And that's, it's times 10 to the -7 there. We could do the 8 there. At this point, it comes in still within the error bars. Well, I think we have that a little later. Okay, it gives us this. 2.99, That's basically where we know it. That's the cutoff. Why do I say this? This is not the exact same number for the estimation because we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 significant digits. We know the speed of light to 9. Take it for what it's worth. Okay. If somebody has better answers, totally open to it. So what we need to do is, because, at least according to Wolfram Alpha, we have the Planck impedance, we have that 2 there. Might there be a geometric articulation that could get us there? Because from our last impedance, we only had, where was it? All right. So up here, we have it to, it goes wonky right around here. So the 3, so we need a couple more decimal places. So let's do a calculation. How do we do that? I don't really know how, but Wolfram Alpha does. You basically use like high school maths, like algebra and stuff. Because what we're looking for here is okay. So what we do now here is I put in the value. It goes to that 2. This is technically in ohms. We don't want to confuse it too much. Doesn't always play nice. But okay, I add some extra zeros to expand our search territory, assuming it's all zeros. I don't think it is. And then we take it to our calculated number, which we have over here. That's from right up there. Multiply by 1 and this is our actual inversion boundary, and we search for x. So what comes up when we search for that? I saw this number and was like, oh, that's a really cool number. You do this stuff enough times, there are certain values where you're like, I think I've seen that before. Why do I say this? And we search for it. Okay. Basically, with no jus, which is part of the hyperbolic Mobius connection equation, or I prefer hyperbolic Mobius partition function. What are we doing? We're partitioning a sphere, or a spherical-like object, I would claim. There are other videos on that, and we'll get into that later as well. Not in this video. So I look for cool things. We found some cool things. I'm like, oh, this was a pretty cool one. That's 5, so that would be our n dimensions times 4 times the mean line inline tesseract thingy to the, I think it's the 4th one there, raised to 5. That was cool. This is also really cool. I actually haven't even tested this one yet. This is with no jus. Oh yeah, and look. Oh look, the Gates constant figure 8 knot volumes. The square root of 3, which is also the cosecant of the magic angle. Times 5, which is our number of dimensional ingredients. And then effectively times, divide by 2, because that's 2 magnitudes of that. That is one really liked one. Oh yeah, and when we just do Joe 1, we get 15 over the domino tiling constant. Which is probably the best. It hits it very, very well. We'll get to that in just a sec. Hey, Thomas! What's going on, brother? It's a job. Job usually infers you're getting paid for something. I'm getting paid with knowledge right now. And occasionally some folks from Patrons. Shout out to my patrons, Joe Franco and Dave M. I'm going to say T Carr as well, because I think he's somewhere from Patreon. But whatever, it's all right. And all you who are watching now, and temporally in the future, thanks for swinging by. I am a crazy person on the internet, but if there's one thing I've learned from spending enough time on the internet, it's occasionally crazy people are right. We continue. Okay. So we went through those guys right there. I don't know, it's pretty notation that a lot of folks don't really understand. Just know it's just stuff doing things. So all you need. A Paris constant is also a good one. That's kind of a measure of velocity. I think there was. Hold on, let's zoom out. You don't need to bore you all with my searching the computational universe. Those don't really want to. Oh, f of f. This isn't a best fit answer, but I didn't include it. Why? That's a Fibonacci factorial function. It's literally for the Fibonacci series. It gives you an answer that looks kind of like that. Okay. It was by itself, and it fit pretty well. So, some Ramajan function. Oh, the square root of 5 dimensional ingredients, I would infer. The Sierpinski constant. It's kind of like something to do with those crazy triangles within triangles and everything. Divide by 3. Well, it almost looks like there may be, and again, rampant conjecture on my part, something about that Planck impedance, that ohms, that oscillation, vibration, that stuff going on there. It seems when we get something like light going into it, or if you divide it, you can basically get the inversion bound. Basically, when you shove light into that inversion boundary, you get this. That's the claim. Wait a second. Is this the reason why we can have matter and stuff? I don't know. Again, rampant conjecture. Good to see you, Sully. good to see. I'm sorry, my schedule is all wonked up right now. I'm still trying to get a feel for the stuff going on, and we get about 3 to 4 hours of math camp a day. The amount of notes I've taken is more than I've done in probably like the past decade or maybe even two. Oh God! So when you realize you're going on, I haven't taken this many notes in 2 decades. It's like, oh wait, when did school finish? I'm like, did I even take that many notes then? Let's actually get to the answer so we can finish up this video. So, okay, current best fit guess. That should actually be guesses. All right, so what's this one? Literally, I take the thing we had calculated up there, I throw the dimension, the thing, the ohms, and then we do that 1 plus r. That's just the numbers of that first answer there. Don't worry. I've been working on some notebooks. You should have the website up by the beginning of the year. You'll just be able to see all the symbology and stuff like that and be like, all right, it's this stuff and it's doing that thing. What's the thing? Maybe a circle. Maybe it's doing a sphere thing. It's actually pretty much, that should be part 2 of this. So we have our 15 divided by the domino tiling constant. I just literally just write it out there. And Wolfram Alpha is very nice, and it acquiesces. I literally could just write the thing. Multiplies that there. Okay, gives us that. We'll speed through this. This one is square root 1/2. Okay, so 1/2 to 5 times the square root of 3, or the magic angle. Of course, the magic angle times the Gießkann constant. Gives us that answer. Our next answer has that Fibonacci factorial thingy in there. And then our Sierpinski constant. We have that 5 all divided by 3 all square rooted. There, okay. Let's go to the receipts. Where are the receipts? Okay. Here's the Planck impedance. According to the thing, just Wolfram Alpha. We just literally go all the way back up. Boom. Just literally write it in. Okay. Nope, it was right after this. All right, there. See? We did the thing. The Planck electric impedance, whatever that is, gives us this number here. All right. And then we'll verify. Well, it ended with what was it, a 2? It's an 8 and a 2, because speed of light ends with an 8, and this we have a 2. Okay. This is the thing according to Wolfram Alpha. Again, take it for what's worth. Apparently some folks have cited Wolfram Alpha. I believe Professor Gupta in the paper where he was like, well, if the universe as we know it is like twice as old. A lot of people disagree. Some folks, including Joe Rogan, may or may not have jumped to some conclusions. I don't know. Okay, so when we use that 15 over the domino tiling constant and a Joe 1 there, we get this answer. Okay, 29.979245 2. Oh, you're wrong. What are the next 2 digits? 9. I don't know about you, but when I went to like grade school and stuff, they told us to round up. That looks like, I'm just inferring potentially maybe that would appear as a 2 according to our detectors. I'm just saying. With using nojas there, part of how we would decompose a spherical-like object, 5 times square root of 3, or you could write that as a cosecant of the magic angle, times the Gießkann constant, the minimal 3 manifold, all divided by 2. 5, 8, 1, 9, 8. It looks a lot like it could be inferred as a 2. Fibonacci factorial, not quite as good, but ends with an 8, 1, 8. Okay, maybe it is, maybe it isn't, I don't know. And the Sierpinski constant in this construction here gives us a 2 and then a 0. So yeah, just a little something we've been playing around with, and got a lot more interesting things coming, but all this different stuff out there, all these different constants of nature, all this jazz, it's, again, you just boil it down. What are we doing? We're talking about stuff doing things. And we're just trying to be less wrong. Why? Because we're all wrong at some point or another. I'm wrong about most things. Am I wrong about this? Probably. But again, every once in a while, you never know where a good idea may come from. I know I've got some pretty good ideas from some of the folks here and some of the folks that may be watching in the future. So that's all we got for right now. Peace out, everybody. Take care of yourselves. It's a wacky and wild world out there, but the best yet to come, I claim. Peace out, everybody.